So where we left off, I was trying to show you that when you have a stringed instrument, that when you pluck this thing, you're not only hearing this one, which is the fundamental, which is a half a wavelength long, you're also hearing the second harmonic, the third harmonic, the fourth, the fifth, the sixth, and the seventh. But they're all added together and it's not obvious. So to hear how loud the second harmonic is, what I'm going to do is I'm going to put my finger right here in the middle of this thing, going back and forth like this. That will deaden or dampen out the first harmonic, so you'll hear just the second harmonic. In reality, if my finger's here, you're also going to hear the fourth harmonic, and you're also going to hear not the fifth, but you're going to hear the sixth harmonic as well. But they're not going to be quite as loud. The loudest will be this one over here. So listen what happens when I put my finger right there, which is the 12th fret of this guitar. That leftover sound is the second harmonic. If I want to hear just the third harmonic, I'm going to put my finger right over here, which is 1/3 from this end, 2/3 from the other end, which is the 7th fret right over there. Listen. You notice it's higher because that's the third harmonic is 3 times higher than the fundamental. Now if I want to hear just the fourth, sure I could put it at the 12th, but I'm also going to hear the second. But if I put it over here at 1/4 the distance, I'm actually going to hear the fourth one. Listen carefully. So that's the fourth harmonic. If I want the fifth harmonic, I go to 1/5 the distance and so on. The point is when I pluck a string, I'm getting all those vibrations. I'm not getting all the stuff in between these frequencies because they don't constructively add together at the right points. So the only sound that really sustains are the one that constructively add together, which is their multiples of your fundamental, your second harmonic, your third harmonic, and so on. Okay, showing another example of wave interference right here. This could take a little while in coming up. All right, yep, I clicked on it. Oh, there's my blue circle. And in 12 minutes, it'll come up. Don't worry. It's spinning. It's working hard. It's working hard for the money. Maybe we're not paying enough money. I don't know what's going on here. A lot of people getting their news out of the way. Maybe getting on the FET this morning. I don't know. And here we go for the interference. So this is a huge deal on what's a wave and what's not a wave. Because back in the day, we're trying to figure out what is a wave and what isn't a wave. Old Isaac Newton thought that light, for instance, was a particle. Why would you think it's a particle? Well, it bounces off of things, just like a tennis ball would. I know they didn't have tennis balls at the time, but they had examples of things bounce off surfaces. And light optically does kind of bounce off things. But what's different about it is that if I got drip, 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 and I start another drip, 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 drip going, you notice what happens. There's a different pattern that evolves. Here we have very strong black, very strong blue. Well, very strong black, remember, is the trough. So this is trough on trough. This is constructive interference where trough meets trough. This is constructive interference right here because this is when peak meets peak. Look how blue that is. That's bright blue because that's where the peak is meeting peaks of these, both of these. So that keeps it a bright blue because that's peak meeting peak. This is constructive interference. Here it's all blurry. The reason it's all blurry is at these points along here, we're adding a trough plus a peak. Well, a black plus a bright blue is a so-so blue. This is destructive interference. Now watch what happens when we change the frequency of this thing. So now we've changed the frequency of this thing. Now you have a different pattern. You notice when it happens more often, it narrows. These destructive interference paths narrow. So what would happen is if this is a wave, you would have basically no wave here, a wave here. So if this was happening in a wave pool, maybe at Oceans of Fun, it's fun here because you go woo, down, up, down, up, down. What would you do here? Nothing. You just sit there in your inner tube and do nothing. Not that exciting. just be taking a break. Because here, this is destructive interference where these meet. So this happens not with particles. Particles hitting each other or can't form constructive and destructive interference. This is wave behavior. So when a dude did this back a couple hundred years ago, well, he actually used light for this thing. So there's our light. Let's go ahead and start the light. Well, there's one, there's two. So you found that light actually does the same thing. And so by light doing the same thing, having these patterns like this, that shows that it's a wave pattern. Anything that's a wave has this kind of behavior. It's called constructive and destructive interference. Now watch what happens if we change the purple, go into a higher frequency. So higher frequency gives us more, right? So you have more of these things, but they're closer together. A lower frequency slows it all down, but it makes them a little wider and we have less of these things. So if we had a screen on the wall, we'd see a big bright spot on the screen here, bright spot over here, and a bright spot here, dim spot right in between here. Because that's where basically the light energy is canceling out and there are no spots over here. And that's what he found out when he projected this on the wall. He found some bright spots, dim and bright spots, saying that, hey, waves do that with water. So if water does that, that must also make sure that's a wave. Sound, it doesn't matter if it's sound. So how to make sound, this cone pushes out, makes the high pressure, pushes out, makes the high pressure, pushes out, makes the high pressure. As soon as it goes back, it makes the low pressure, which is the black. It's the exact same pattern. So a wave is a wave. All waves behave the same. They have the same wave characteristics, which you could use your wave equation. The velocity equals wavelength times your frequency. It all works the same. So they all have the same rules of how they interact with each other. So waves are a way to transfer energy, but the particles themselves don't move. So if I could actually put particles in the air right now, there you go. So the particles don't have a net displacement. They just kind of go back and forth, but we still have patterns of less movement and more movement. So we still have those things going on. This is a longitudinal wave in reality when we do sound. Now if I do light, it shouldn't do any, you don't have any particles. Okay? And if I do the wave stuff, we don't have particles once again, but with sound, you actually have particles of air because that's how the information gets transferred. So you notice the net molecules of air don't go anywhere, just the vibrational energy does go somewhere. Okay, one more thing to talk about. Alrighty, so that's interference. One more property of waves, and that's the Doppler effect. Okay, kind of a fun one. So you've heard of the Doppler thing, Doppler radar maybe. Well, it's a change in pitch caused by the motion of a sound source. Well, it's not just the change in pitch for sound, it's a change in color when we're talking about light when things move around. So this happens with all waves, not just sound, all waves. So why do we observe this? Well, let's check out one more thing. It's a jet. Who doesn't love jets? Okay, here's a jet that's going half the speed of sound. That way, look at that. Woo, look at her go. Now you notice it's scrunchy in the front, long in the back. It's kind of like a mullet. Short in the front, long in the back. Here's what you'd hear. So let me repeat this over and decide, try to model what you would hear if this actually had sound. So the reason this happens is sound can only travel so fast. The only way to make sound travel faster is to change the medium, like heating the air up would make it travel a little bit faster. Or if you cool down the air, it would actually travel a little bit slower. So it turns out where airplanes fly, it's cooler up there. The speed of sound is a little bit less, it turns out. But that doesn't have anything to do with the Doppler effect. What happens is, as this thing is making noise or vibrating going through the air, that vibrations, they travel outward in the air at about 350 meters per second. So a little over 700 miles per hour, maybe 720 or 30 miles per hour. Up there where it's cold, it might be in the upper 600s, but still. So the speed of sound in the air is going to be about 700 miles per hour. Well, if this is going half that speed, 350 miles per hour, it doesn't catch up to the sound because the sound's still going away from the thing at some speed, but it's also looks like it gets longer in the back because it's also leaving from where it used to be. So what happens, it makes it look like, not just look like, but it actually makes the wave scrunchier in the front. So here's what you would hear. Say this is an ice cream man coming by, and he's ringing his little bell coming by. Doot 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 doot. So what you're gonna hear, you don't hear anything yet. Now you hear it. Doot 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 doot. You notice the sound pitch drops because the wavelength is longer. The speed of sound hasn't changed, but the apparent frequency has. So the reason why the apparent frequency has changed, it's a term because it's getting squished in the front, long in the back. So you get actually what's called a Doppler shift in pitch or frequency. But it happens not just with sound, it can happen with light. You don't notice with light unless you're going near the speed of sound, like half the speed of sound, half the speed of light. You wouldn't notice this. But things that are traveling fast, I mean, they get scrunchier in the front because the waves can only travel so fast. Now let's go at almost at 0.9. Almost the speed of light, 0.8789, there you go. You notice what happens? It's getting very scrunched up here. So very scrunched, and that's very scrunched along here and very long over here. Now keep in mind, this is a longitudinal wave. So I'm going to call the purple the compression, which is the peach in the middle is going to be called the rarefaction, the spreading out. So this is the compression, and this is the spreading out. Let's actually go the speed of sound. So it happens when you go at 0.1, Mach 1, which is the speed of sound. And bam, oh, I'm going a little over. Speed sound, there we are, close enough. Notice what happens, guys. When it's flying at the speed of sound, the compressions are on top of each other. So if I'm the arrow, what would you hear? Bam! That would be, that bam was actually a sonic boom. You notice the sonic boom's not over here, you only get it once. Because it's basically the wake over here. When you take compression plus compression plus compression plus compression, that is a super compression. It's so compressed right here, that's what makes your sonic boom. So that's what happens when you're braking, you're at the speed of sound. Now the first few people, couple people who flew the speed of sound, at least on record, didn't make it. They ended, because in one case the wings fell off, because what happened is, this is a high pressure wave sitting right on top of the airplane, and they lost control of the airplane in both cases. Chuck Yeager, the first person to break the speed of sound, did something a little different. Put down the throttle and kept going faster. So let's go faster than the speed of sound now. So if we're going faster than the speed of sound, look what happens. Your plane actually gets ahead of this. And what would you hear if you're standing over here at the arrow? Nothing. Well, if it kept on going, as soon as you hit this, that would be another bam, because that would be another boom, because this is a wake. And the faster this plane goes, look what happens to the wake the faster this goes. Let's go at over Mach 2. Come along, you're the arrow. Bam! So once again, that would be the sonic boom, because we're adding all these two things, these together right here. This is additionally a lot of compression of the air. That's where the sonic boom is. So you still get a sonic boom. You don't get a sonic boom just when you pass it the first time. It's always there. It's the wake. Some of you boaters out of there may have seen this exact same pattern, because that's what happens with boat waves. Is with boat waves is you also make a wake behind you. And so I used to have a boat, and there's a place in the dock where it's a no wake zone. Well, no wake zone means you have to go slower than the speed of the waves. And as long as you go slower than the speed of the waves, you don't really quite make a wake. You can't see this because the lines are fat, but I'm not really making a wake right over there. So I'm going slower than the speed of the waves. But as soon as I go faster than the speed of the waves, I make a wake. And here's a pretty broad wake right over here. So if I'm a wake, like to jump on my wakeboard, jump that wake, that's going to be almost impossible for me to jump. That's a huge friggin' wake. So I never went that slowly. One, my boat didn't go very slow at that, making a nice wake. I need a narrower wake. So what I did is I went faster than what a lot of people do. And when you go faster than what some other people do, it narrows the wake. So if behind the boat I jump this, because I get a big wave here that I jump and I try to land on the back side of this is a nice ramp to come down by. Even that's a long way for me to jump. So I had my boat going a little faster than that, than what a lot of people did. So I didn't have a big wake, but if I hit it faster, I'm flying further anyway. So there's my wake. Now that's a nice narrow wake. I could easily jump from one side to the other side with that one. So the point is, a boat makes a wake behind it because it's traveling faster than what the waves can actually travel. You get the same thing. So this Doppler effect happens all kinds of places. It happens with light. So a galaxy coming towards you, it's going to be if a galaxy is coming towards me, it's going to get scrunched up light in front, which is a blue shift. If a galaxy is going away from me, that's a red shift. It's going away from me.